Okay, so we are nearing the conclusion right now. As you can see, let us recollect the big question. What is the question? When you assign values, gold coins or resources, whatever you call it, to all the nodes, and as you start sharing them, respecting the edges that leave a vertex and then enter a vertex, right? A directed graph, you will observe that the values do indeed converge, right? So let us take yet another example and then see it. We have already seen an example on 3 nodes, another example on 5 nodes. We'll see yet another example for clarity's sake. So let's consider this graph on 4 nodes. This is the corresponding matrix. We have discussed this before, right? Take a minute's time, pause the video and then check this is actually the matrix. Now, let me write down this matrix as a matrix. Then I start off with 1 by 4, 1 by 4, 1 by 4 and 1 by 4, and then I see where it takes this. 1 by 4, 1 by 4, 1 by 4, 1 by 4 simply becomes 1 by 8, 3 by 8, 3 by 8 and 1 by 8, right? So we know this, right? We saw this. Now let me write a table and then make a note of all the values here, A, B, C, D, and then I started off with 1 by 4, 1 by 4, and then I got this. What is the next value? Where does it go like this? Where exactly does it converge? So here is a quiz question for you all. Take a minute's pause and then see that it indeed converges to 19 by 100, 1 by 3, 19 by 50, 9 by 100. In fact, you need not even take a look at these values. You should verify that you actually arrive at these values as you proceed with this matrix operation. Alright, a quick quiz for you all. It's good that you check it. Now, as this goes further, you know this assignment is now what is called a stable assignment because it doesn't change anymore, right? You assign these to the nodes A, B, C and D. You assign it to A, B, C and D. Assign what? Assign these values and you will observe that there is no change anymore after this. Okay. So, it remains the same. Correct. So note something. Here is the situation where A alpha becomes equal to alpha, and that is why the change doesn't happen, or rather the change doesn't happen because A alpha equals alpha. It's all the same, right? So this is the matrix way of saying it, right? Okay. So consider the graph once again and the assignment. You will observe that this is the assignment where values don't change. You can try doing it when A is assigned 19 by 100, B is assigned 1 by 3 and C is assigned 19 by 50 and D is assigned 9 by 100. The values do not change after that. And such a value, such an assignment is actually unique. And we all have seen it already. I am sort of reiterating it right now in this lecture video. Why does it converge? Why exactly is it converging? Now, isn't that obvious? We have seen that enough. Take the matrix. Note that, what is this? What do you understand by this? Have you seen this matrix sometime before? If you are an engineering student, I don't think you would have passed by your semesters without noticing this matrix. Right? So any student who has finished his first 4 semesters of engineering would have definitely passed through a phase where he would have encountered this matrix. It is actually called the Markovian matrix, right? So observe the property here. Every column sums to 1. Such a matrix is called a Markovian matrix or simply a Markov matrix. So this Markov matrix is a very interesting property. Its highest eigenvalue is simply 1, which means every other eigenvalue is less than 1. Alright? Okay. So do you see what happens here? Let's go slowly. A to the k of v is simply this. where v1, v2, vn are all eigenvectors and lambda 1 etc. are all the corresponding eigenvalues. Good. So we can always write A's action on V can be captured with this. So we have seen this before. I am repeating it. Okay. Next. Lambda 1 is 1 here because that's the highest eigenvalue, as I told you. That's the property of such a matrix. And the other eigenvalues are less than this. Now what does it mean? Now you would have observed a number which is 1 to the power of k will make it 1 itself, right? Other numbers are less than 1 here, all these are less than 1 here, and when you raise it to the power of k, all of them become 0, right? All of them variably become 0. So a to the k will simply be equal to lambda 1 to the k times v1. Mind you, lambda 1 is actually 1. So this is the eigenvector corresponding to the highest eigenvalue, which is 1. And let me just remove lambda 1 here because it's equal to 1. So what do we observe? We observe a to the k of v converges to the eigenvector corresponding to 1. Okay, perfect. That's pretty much it. We have come to the conclusion. So this was the graph that you took. You saw this was a sort of a stable assignment, which means it converges at this value, and now it all makes sense, as you can see, right? So such a value assignment is unique, and no matter where you start from, you always converge to this. So that's the best part. So that sort of concludes good amount of discussion on PageRank. We have revisited PageRank from our previous lectures about some 20 lectures ago, a couple of weeks ago, roughly let's say 3 to 4 hours of videos before. We saw PageRank very at a very conceptual level. We did not see the math part of it. We have now seen the math part of it. I hope it's clear to all of you. It is important for you all to take a look at it, maybe rewatch the videos, because it takes time to sink in, especially the mathematics component of PageRank.